So now that we have our basic definitions, we're gonna end up deriving. We're gonna end up talking about 4 fundamental equations that you'll learn now and remember for the rest of your life. All right, and we're gonna sort of derive these, but I'm not gonna dwell too much on the derivation because that's not all that important. I just like for you guys to know where things come from. But before we get into these equations, let's look at three different cases of motion, so that we can sort of build up. And so the first case that we're going to look at is the case of constant position. The second case that we're going to look at is constant velocity. The third case that we're going to look at is the case of constant acceleration. Now we're going to study those 3 cases of motion, or at least we're going to talk about them. So let's jump right in and let's look at case number 1. Constant position. All right. So the case of constant position, it's so interesting. No, it's actually really, really boring. We're not going to talk about it at all. It's really boring. I mean, the only thing that you have to know is that, well, if you have constant position, then you know that the velocity must be 0. If the velocity is 0, the acceleration is certainly 0. The thing that you're talking about is not moving. It's just sitting there. That's not really all that interesting. Like you guys are just sitting there. You're not very interesting right now. Okay, so constant position is really boring. That's all we're going to say about it. I just, for completeness, we talk about constant position. So let's get into constant velocity then. Constant velocity, that case is a little bit more interesting, all right, because now we actually have some movement. But if an object is moving with a constant velocity, then its position is changing by the same amount. During each interval of time. But it's not just the same amount, it's also the same direction. So the same amount and direction. All right, so during each time interval that you're observing some object, let it be a ball that's moving at a constant velocity, its position then is changing by the same amount and direction for each time of interval that you take a look at this thing. And so let's just draw this sort of as a series of time intervals then. Let's look at time equals 0, time equals 1. We're sort of using arbitrary units. Call them seconds if you want. Time equals 3 seconds. And I'm going to draw a series of lines here. Let's see if I can do this. We have an object. Starts off at this position. We'll call it position 0. It doesn't really matter. At time t equals 0. All right? If it's moving with a speed of 2, again, sort of in arbitrary units, that means it's going to move at time equals 1 to that position. So it moves this far, 2 spots, 2 positions, 2 meters, if you want to say that. So let's say this is 2 meters, right? In 1 second, it moves 2 meters. So this is 2 meters per second, sorry. All right? In between time t equals 1 and time t equals 2, it then moves to this position, another 2 meters. And then finally, once we get to the next time interval, it moves another 2 meters. Okay, so just reinforcing the idea here that as we step through time, the object that we're following, each interval of time moves the exact same amount. Okay, so there's nothing really that crazy here. And knowing that, we can write down an equation that describes position as a function of time. Now, you've already seen an equation that describes position as a function of time. And I'm just going to write it down in a slightly different form. So if I take the change in position, so x minus x naught, and the sort of lingo that we've been using, that's equal to the velocity, which is constant in this case, times t minus t naught, or the time difference. And remember I said that I usually write that, typically this, we just sort of shorten this up, and we always treat t naught as 0 because we can sort of say t naught as whatever we want. So this is sort of the equation that we're most familiar with. All right. Now this looks exactly like an equation you saw yesterday, right? I mean, this is just the change in the velocity is equal to the change in position divided by the change in time. It's just v is equal to x divided by t. Right? So if you've already seen that, I just wrote it in a different way. I just rearranged it because it'll look more like the other equations I'm going to write down in a little bit. And the other part of this is since we have a constant velocity, that means that our acceleration is 0. All right. So this is the case of constant constant velocity, 0 acceleration. So it's a little bit more interesting than the position case, but not all that much. All right. If you know the initial position of an object, you know the velocity. After some time interval, you can determine where the particle is at some later time. So imagine, you could apply this if you're driving in a car at a constant 80 miles per hour down the highway. You say, okay, how long until I'm at Battle Creek, 80 miles away? Well, it's just v times t, so it's 1 hour, okay? You guys probably do that calculation all the time in your head. We'll just put a formal equation around with it. All right, so now let's jump into the more interesting case of constant acceleration. In the case of constant velocity, if our position is changing the same amount during each time interval, how do you think then that the position, in the case of constant acceleration, the position will change in the same amount during each time interval? What do you think? Yes? No? So I have constant acceleration. Will the position change by the same amount? Can I basically draw what I just drew? It's going to look the same. Right, it's gonna look different. So it's gonna look a little bit different. So let me say that. All right, fine. So if we have a constant velocity, that means that our constant acceleration. That means that our velocity is changing. So let me just start off in the case that we have a velocity of 1. All right. What that means is in the interval from time equals 0 to time equals 1, well, I move 1 position. But if I'm accelerating at a constant rate, that means my velocity is going to increase during each time interval. So from the time interval between 1 and 2, my velocity is now 2, which means I'm moving 2 spaces over on my timeline. And then now my velocity becomes 3, so I move 1, 2, 3 spaces over. All right, so as time evolves, my position gets the difference between positions between 2 successive time intervals becomes much, much larger. All right, so this is the case of constant acceleration. Up here, when we're dealing with constant velocity, the relationship between position and time was linear. Okay? The relationship between position and time for the case of constant acceleration is nonlinear. But let's start by taking a look at how velocity. It is. Is the mic on? Yeah, it is. How does velocity relate to acceleration? So from yesterday, we learned about how velocity relates to acceleration. Who can remind me really quick? The right side of this equation, what's it look like? Acceleration times time. That's good. Right, so the change in velocity is equal to acceleration times the time duration between these two measurements. All right, so again, I've sort of shorthanded t as t minus t0. In other words, I treated t0 as 0. We're just going to say that's 0. All right, so this is our equation for the change in velocity as a function of acceleration. Now, remember, everything that we do is going to pretty much deal with constant acceleration. And constant acceleration problems actually exist in quite a few places in the real world. Okay, everything that is falling is undergoing constant acceleration as long as it's not moving too quickly. Generally, cars sort of accelerate with constant acceleration. When we speed up from a standstill to a running, we're usually accelerating at a constant rate. So even if it's not perfect 100% of the time, it's a pretty good approximation to real-life motion most of the time. So that's why we spend a little bit of time doing these sorts of problems. So I already know one equation. I know that I can relate the change in velocity to an acceleration. Another thing I can do is I can relate the change in position to time. All right. So from our equation up above, we said that the change in position is related to velocity times time. Now that's not true in this case unless I make one slight little adjustment. Okay. So in this problem up here, for example, we could say that this object started with initial velocity of 0 and accelerated to velocity of 3 meters per second. Okay? So it wouldn't be correct to say that the change in position is equal to 0 times time t. That wouldn't make sense because then the change in position would be 0. Right? This velocity is changing as time elapses. So any ideas what I might put here instead of just v? Right? It's got to be some sort of velocity, but what velocity might I use in this equation? Yeah, the average velocity. Right? So the average velocity is the one that we really care about because, well, it wouldn't be right to use the initial velocity, or 0, because I know that the change in position isn't 0. Similarly, it wouldn't be right to use the maximum velocity. So it's got to be somewhere in the middle. And since we're accelerating at a constant rate, it's the average velocity. That's how it works out. And so I can use the average velocity here to work with this equation a little bit. And that's what we're going to do. We're going to actually work with this equation just a bit. So what I'm going to do is I'm going to write down the average velocity in another way. When I'm undergoing a constant acceleration, I can write the average velocity like so. It's equal to 1/2 times the initial velocity plus the final velocity. That is the average velocity. Okay, it's just the velocity in the middle there. All right? If I write it like that and then take a look at this equation up here, what I can do is I can substitute in an equation for this v. So I want to solve that equation in terms of v. If I do that, it's pretty straightforward. It's just v naught plus a times t. So I'm going to take that v and I'm going to put it right there. And so what I get is v naught plus v naught plus a times t divided by 2. That's my average velocity. All right, and if I just go ahead and do a little bit of factoring and combining terms, what I'm going to end up with is a v naught plus 1/2 acceleration times time. All right, so that's another equation for v average. You don't have to remember that one or anything. I'm doing it so that I can use this term right here. Okay, but this should sort of be familiar, and that's something you should stick in the back of your head. Yes?
So you have 2 v naughts there?
I do, so I combined them
Okay.
into a 2 v naught, and then I divide it by 2.
But then why is the 1/2 still there?
Because that has to go on this term. So if I write this out, it's 1/2 v naught plus 1/2 v naught plus 1/2 at. Okay, no problem. All right, so now that I've got this thing, I've got a v average. I'm going to take this equation and just plug it in right here. And what I'm going to be left with is x minus x naught is equal to this thing times t. Okay, so I'm going to get as v naught times t plus 1/2 at squared. All right, and before I go any further, I'm going to make note that t, it looks a heck of a lot like plus. So I'm going to try very hard to make my t's with the cross on the top half and my pluses small. So I apologize for any confusion, but just keep in mind that sometimes pluses and t's look very, very similar. All right, I'm going to do one more thing to this equation just because I like to have it in this format. And this is how you'll see it in most books. X equals x naught plus v naught t plus 1/2. That's a 2. That's 2 halves. Let's do 1/2. Let's do it right. 1/2 at squared. All right, so this is a very, very important equation. This shows how position is related to time as a function of for the case of constant acceleration a. Okay, and what I said before is that the relationship is nonlinear, and that is obvious here because the relationship is actually quadratic. There's t to the second power. Okay, so I'm happy it's not linear. Yeah, Cheats.
So you said it shows how position is related to time.
How position is related to time for the case of constant acceleration. Okay? For the case of constant acceleration. Now, don't get hung up on that constant acceleration case. All right? We talked about 3 cases of motion. We said for constant position. Does this equation work for constant position? In other words, the case when v is 0 and acceleration is 0? No. Oh, come on. No. Yes, it does. If v is 0, I just say that's 0. If acceleration is 0, I say this is 0. So let me write it out for you. Constant. No, you're just saying no because you're just like, I want to say no. You didn't use your brain there at all. Let's look. Okay, here we go. X equals x naught plus VOT plus 1/2 AT squared. For the case of constant position, I said that V is equal to 0, A is equal to 0, which means if those things are 0, that goes away, this goes away. Oh, surprise, constant position. The position doesn't change. Okay, so yeah, this equation, while holds for constant acceleration, also works for the other two cases that we just talked about. Right? So this is fine. The only assumption is that the acceleration is constant. Note A equals 0 is a constant acceleration, so that's fine. This will work. Right? So you don't have to remember anything else I just told you. Just remember this. Right? Now this is the equation that you want to use to find position. Now that's one equation. I did actually, there's a couple more equations up here, so let's actually write these down in sort of a nice little format. Well, let's do that in a second. I'll point them out. All right, so I have these two equations right here. This relates velocity to acceleration as a function of time, position to velocity as a function of time. So these are also two of the equations we're going to use. I'm going to summarize them for you in a nice little box with a square around them in just a second. So that's 3 of the equations that we're actually trying to get out of the 4. The problem with these equations is if you notice, each one of those has a t in it. It would be nice if we had an equation that didn't involve time, in case we didn't know time. If that's that's one of the unknowns. So let's try to get an equation where we don't need to know time. So in order to do that, what I'm going to do is I'm going to start with this one that you've already seen. Again, I've just rearranged it a little bit, moved the v naught on the other side. I'm going to solve that for time. It's equal to v minus v naught divided by a. All right. I also have another equation that we worked with already, which was x minus x naught is equal to v av times time. And I'm going to go ahead and I'm going to leave that like that. And what I'm going to do is I'm going to plug time in over here. Okay, so I know that x minus x naught is equal to v av. V av already told you was v naught plus v divided by 2. All right, so I'm going to multiply that, and then I just solve for time right here. So I want to get rid of time. That's what I'm after. That's v minus v naught divided by acceleration. Okay, so all I did is, again, I just took this equation for t, plugged it in over there, used what I already know about the average velocity, plugged it in. And if you do all the, what is it? Is it FOIL? Man, it's been so long. But if you do all that stuff, what you get is v squared minus v naught squared divided by 2a is equal to x minus x naught. All right, and if I rearrange that, because that's how we roll here, we'd like to have things in a similar format. What I get is v squared is equal to v naught squared plus 2 times a times delta x. All right, so this is just a delta x. All right, so now I have another equation, number 4, a nice equation that is not dependent on time. And that's what I was after. All right, so let me go ahead and summarize all those. These are important. You will be using these a lot. This will be the meat of your first exam, using these equations. And again, these are all for constant acceleration. Remember, 0 is a constant. Constant acceleration, we have v squared is equal to v naught squared plus 2a delta x. A lot of the times you'll just see this written as x instead of delta x, which just uses the assumption that x naught is 0. Okay? Write it however you want, but understand that that this should be a difference, even if one of those numbers in the difference is 0. Another one of the equations that we've seen, v naught, that should be equals, is equal to, let me start over. V is equal to v naught plus acceleration times time. The one we just derived a minute ago is x. The position is equal to x naught plus v naught times time plus 1/2 at squared. All right, and another equation for position was x is equal to x naught plus the average velocity, just like I have written right here, and I'm just going to write it in a slightly different form. which is 1/2 v naught plus v. So that's the average velocity times time. So I just took this term and included it in this equation. All right, so we have these 4 equations.
Wouldn't there be a 1/2 in front of the AT at the bottom one?
This one?
Yeah.
No. Remember, this came just from our initial definition of velocity. Oh, I'm sorry, of acceleration. Acceleration is equal to velocity divided by time. So here's the 1/2 over here. That came about because we were doing some crazy substitution of different terms. But acceleration is equal to the slope of the velocity versus time plot. Okay, so that's a basic definition. The 1/2 term came in right here, where we are writing this as v average. So this is v average, not just the final velocity of some particle, okay? So this is, throughout some trajectory, we have an end velocity or a starting velocity, and the average velocity is the 1/2. That's why I said sort of ignore that equation. We're not going to really use that. Okay? So those are the 4 equations that you're going to use, and all we're going to do for the rest of today and then and probably a little bit tomorrow post-quiz is to use these 4 equations. That's the physics. So the physics is actually, the physics is done. We've done the physics. We came up with these equations, we related them to the definitions of velocity and position and displacement and acceleration. Just applying these equations, well, unfortunately, that's the hard part, but that's what we have to do next. Did you have a question? Nope, you're good? All right, sweet. All right, so let's apply these. Let's apply these in form of an example problem. And let's move over and do a different color. So here's an example. I like space, so I often bring in rockets. So let's use a spaceship this time. So we have a spaceship. So a spaceship that's initially traveling at, what did I say? Oh, it's initially rest. Initially at rest. Ooh. Read my problems before I write stuff. Initially at rest. And that thing, it accelerates. It does accelerate. Accelerates at 10 meters per second. And I want to know what is the velocity after 40 seconds. So what is the velocity after 40 seconds? Okay, so if I draw a picture, the first step in solving any physics problem is to draw a picture. All right, this rocket is going to accelerate. We're doing 1D motion, so it's accelerating in a straight line. And it's going to, we're asking the question, what is the velocity after 40 seconds? So I'm drawing sort of a vertical time axis. I don't know anything about how far it's gone in that amount of time. All right, so the first step is to do 2 things. So step 1 in solving physics problems. So this is sort of this is how I want you guys to sort of do these problems and follow these steps throughout the course, please. The first step is to draw a picture. And I want you to label a coordinate axis. All right, so here we have a picture. We're dealing with 1D motion, so we only have one direction, and the direction of interest here is up and down. And so what I'm going to do is I'm going to label the coordinate axis, and I'm going to call that direction y, because I've drawn it up, so I like y to be up. All right, so our positive y direction, now I'll actually point out this is the positive y direction, is up, which would make the negative y direction down. All right? So once I do that, step 2 is to make a list All right, so make a list of the things that you know and what you don't. So let's do that. So the things that we know and the things that we don't as it pertains to this problem. I'm just going to sort of go down the line here. Out of all the things that we could ask about in this problem, well, we could ask, well, what's the initial position? What's that? Well, that's the velocity. What's the position? All right, well, so in a lot of these problems, sometimes you get to choose. All right, I get to choose. And so when I set up my coordinate axis, I can say that initially the position is 0. So that's fine. We could do that. I get to choose. I could figure out, I could ask, what's the final position? We'll just write that as a y with no subscript. I don't know what that is. I might want to know what is the initial velocity. And you said it was at rest, which it is initially. The final velocity is something I could inquire about. I don't know what that is. I think that's what we're after. I need to know what the acceleration is. I do know that. It's 10 meters per second squared. And if I look back up here, I got to get the units right. All right, so I do know acceleration. And then time is the other thing that I may or may not know. And in this case, I do. It's equal to 40 seconds. All right, so there's a list of the things that I do and do not know in this problem. Okay? Now what that does is it allows me to, makes it a little bit easier to do step 3. Pick an equation. Yeesh. And once you pick that equation, you can solve. So we'll start with step 3, and that's pick an equation. So take a look down at your sheet, your list of 4 equations. I could scroll up, I guess. It's not too far. All right, so what do I know in this problem? Oh, I can't get them on the same screen, can I? So close. So close. All right, so take a look at your list. We have a list of knowns and unknowns here. So what things in your list, what equation will allow you to solve this problem for the final velocity? Remember, we're after the final velocity. All right, so you know you're after the final velocity, you know the initial velocity, you know the acceleration, and you know the time. So that's a good choice. You can use that guy to solve this problem. And so step 4 then is to actually do the solving. If you've made it this far and you haven't made any mistakes, then step 4 should be the easiest part. All right, the hardest part is listing what you know and then picking an equation. That's the hardest part. The solving is just, math. You guys learn that stuff in nursery school. So we know the velocity then is going to be equal to the initial velocity. Well, that's just 0, plus the acceleration, 10 meters per second squared, times the time, 40 seconds. Unless my math is wrong, I do believe that is 400 meters per second. All right, so my final velocity is 400 meters per second. Now, let me ask you this. What am I missing here? I'm missing a direction, because velocity is, yes, a vector. And the velocity is up in my problem, or in the positive y direction, whatever you want to say. Either one of those is fine. Up, positive y, I'm okay with either one. Now you think you're done, but you're not, because there is step 5. And that is to ask yourself, does this make sense? All right, and there's a few things we're looking at here. First, are your units correct? Well, in this case, it's pretty easy to look at that. I had meters per second squared multiplied by seconds gives me meters per second. All right, so doing my dimensional analysis will tell me that my units are good. Meters per second is, in fact, a velocity, the unit for velocity, and I didn't cheat. All right. The second thing is the direction. Does the direction make sense? Well, I'm glad I didn't get a negative velocity, because that would not have made sense. So in this case, it's a little bit easy, but yeah, up makes sense. And finally, does the magnitude of the number make sense? 400 meters per second. I mean, I don't know. In this case, I probably wouldn't expect something really, really small or really, really big. 400 seems reasonable to me. All right? It's not always obvious if it makes sense or not. So that's good. So always take a minute and actually say to yourself, does this actually make sense? It'll save you some trouble on the back end. All right, any questions so far? Do you like that procedure, 5 steps? Lay it out. If you do that, I swear, especially the first 2 steps are the most important. Coordinate axis, listing what you know and you don't. If you get all that stuff right, that'll make picking an equation much easier, and then solving it will be a breeze. So do that. Do yourself a favor and get in the habit of doing that. It will make life much, much, much better. All right, so one of the things we didn't figure out while we were doing that problem is we did not figure out how far the rocket went. So now let's ask that. So how? I see you're getting tired of me drawing. How far did the rocket go? Right? So again, we can go back up. We have the same information. We also have a velocity now. So you may pick an equation at will. If you take a look at your list, see if you can pick it before I scroll down. Oh, God, what's happening? All right, see if you can pick it. If I were choosing, I would pick the equation that says, I'm going to write it. I'm going to confuse you now. I'm writing it. I've been writing all of our equations in terms of x's. Been writing our equations in terms of x's. I'm not using x in this setup. I'm using the variable y for position. So I'm going to use the equation y is equal to y naught plus v naught times t plus 1/2 at squared. All right, so that's what my position is going to be. Now, I know this is nice because my initial position I set as 0. My initial velocity I set as 0, so that greatly simplifies the equation and allows me to quickly find the position. So I had 10 meters per second squared is my acceleration, my time, 40 seconds, and I'm going to have to square that. Let's see, that gives me 160,000 divided by 2 gives me 80,000. Get that right? Did I do that right? 400, what? 8,000, yeah, I'm sorry. I got one too many zeros in there. Getting out of control. Oh, not 8. Not 8. 8,000 meters. 16,000 divided by 2 is 8,000. And you can see I'm left with meters because if I do my dimensional analysis really quick, I have a meters per second squared times second squared leaves me with meters. All right, so 8,000 meters. And the rocket went, I'll just write it in the positive y direction in this case.